The final topic we are going to talk about this week is divide and conquer recurrence relations. And as the name suggests, these are related to divide and conquer algorithms in general, where you divide the problem into sub-problems and you solve some of them, and then you combine the solutions to obtain the general solution. And we have seen last week to how to write recurrence relations for those type of algorithms. In the general context, suppose that an algorithm divides a problem of size n into a subproblems with sizes n over b, and that a total of g of n extra operations are required in the conquer step. And the conquer step, well, it also involves the separation part, the operations required to solve or rather partition the problem into the subproblems, and afterwards combining their results to obtain the final solution. In general, the number of operations required, Tn, satisfies this recurrence relation. Tn equals a times Tn over b plus Gn. Okay, this is straightforward because you need to solve a subproblems, each of which are of size n over b, and then you need additional g of n steps. Okay, some examples here is binary search, as we have seen earlier, satisfies Tn equals Tn over 2 plus 2, or merge sort Tn equals 2 times Tn over 2 plus n. Now, in the general context, b here should be greater than 1. A here should be greater than or equal to 1. It could be 1, but it shouldn't be less than 1 because it doesn't make sense to solve less than 1 problems. And B, of course, should be greater than 1 because subproblems, by definition, should be smaller than the original problem. Okay, so in a more general context, you might relax these conditions, but for practical reasons, we are going to assume those. And usually, the number of operations required for an input of size 1 is going to be assumed to be constant. So in general, we will assume T1 to be big theta 1. It doesn't have to be 1. It could be 2, it could be 5, it could be 11, it could be 100, but the idea is it's a constant. So this is our general assumption. When you have hit the basis condition, let's say, the number of operations required is constant. And let's look at how to solve this on an example, a simple one. Take merge sort, Tn equals 2 times n over 2 plus n, with the initial condition T1 equals 1. So recall merge sort, it's a sorting algorithm. So if your input is just a single number, it's already sorted, so T1 is 1. You don't need to do anything. So what you do is you divide your input into 2 subproblems, into 2 groups to be sorted. And of course, you need to sort them both. So I have a coefficient of 2 here, plus n. Plus n is the merge step, the merging of sorted sub sequences. Now, this is my recurrence relation, and actually I can write this as Tn equals n plus 2Tn over 2, and then this I can write as this, n over 2 plus 2 times Tn over 4. I have just applied the definition, nothing more. And when you expand this, you see 2 times n over 2, you get n also. And 2 times 2 times Tn over 4, you get 4 times n over 4. If you go one step further, you'll get n plus n plus n plus 8 times Tn over 8. And you see the pattern here, okay? Until you reach Tn over n, you need log 2 of n steps, assuming that n is a power of 2 without loss of generality. You will have n plus n plus n plus n plus n, where there are log 2 n terms here, plus n times Tn over n, and this is T1, and based on our initial value, this is 1. Therefore, this is n times log 2 of n plus n, okay? And essentially, this is a big theta n log n expression. Now, I dropped the logarithm here. Well, you see in the big theta expression, I don't need the base of the logarithm anyway. Okay, so this is a very simple case, but this is how we approach divide and conquer relations. And let's see this on a more general case. In fact, this has been laid out in this paper. If you are interested to take a look, it's not really a very advanced paper. Okay, so some steps are glossed over, some are skipped out. So maybe it might require some time to really grasp it, but it's not really a very, very advanced paper. You should be able to understand it when you read it. And this is the main reference for this derivation. So what you have here is A times Tn over B plus Gn as the recurrence relation that T of n satisfies. Okay, so what we do here is a very similar thing, except for this small trick, let's say. Instead of Gn, we write n to the power log b of a, g1 of n. So we are assuming g of n can be written as n to the power p for some p times g1 of n, where p equals log b of a. Okay, it's a simple case of a division, but it's going to make things easier for us. And therefore, you do the same thing, just write T n over b using the definition, a times T n over b squared plus n over b to the power log ba times g1 n over b plus this term. Again, if you continue this procedure, this iterative procedure, until you reach T of 1, again here we are going to assume n is a power of b without loss of generality. And what you will have here is a times a times a, etc. And to reach n divided by n, I need log b n steps. So that gives me a to the power log b n times t1 plus here you will observe that this turns out to be n to the power log ba, this term here, multiplied by this sum, g1n, g1n over b, g1n over b squared, n over b cubed, etc., down to b cubed, b squared, and finally b. Okay, so this can be written as, well, another small trick here, this value here, a to power log bn, and this here, n to power log ba, these are in fact equal. It's not that difficult to show this. If you take the logarithm a of both sides, you will have log bn times, well, the log a of the left-hand side is going to be equal to this anyway, and this will be the exponent times log a n, right? And if you write both hand sides as ratios, log n divided by log b equals log a divided by log b times log n divided by log a. These cancel out. You see log n divided by b, log n divided by b. Therefore, this value here and this value here are equal. N to power log b a times t1 plus this term here. I from 1 up to log bn, g1 b to the power I. So that's b squared, b to the power 3, etc., up to n over b, and finally n. Okay, so this is the general picture. And this is, let me clear this out a little bit. Tn equals this expression here. Okay, so the question is which term is going to be dominant here? Because this we have decided to be a constant value multiplied with this, and this is going to be another factor here. So this might be larger, and it might make this even larger, or it could be a smaller number, in which case this term would dominate. So the general setting here is laid out here, and this is called the master theorem for divide and conquer recurrence relations. And the conditions are given here. If g of n, the function appearing here, if this is big O n to power d, where d here is less than log b of a, then t of n is big theta of n to power log b a. Okay? In this case, the operations required for solving the subproblems dominate. So the merge part, let's say, or the conquer part is negligible, let's say, in the long run, compared to the subproblems. The subproblems need much more work compared to the conquer step. Okay? Therefore, this is um, the term that dominates. On the other hand, if g of n is big omega n of d, meaning that it's lower bounded by n of d, where d is greater than this exponent here, and this is satisfied where we call this the regularity condition. In this case, t of n is big theta of g of n. Okay, so in this case, the subproblems, the solution to the subproblems becomes uh, negligible, let's say, for large inputs, uh, when compared to the conquer step. Okay, in this case, the operations required for the splitting the problem into subproblems and then merging their solutions is the dominant factor, so that g of n dominates, and therefore your function is big theta of g of n. And there is a third case, or rather a second case in between. In this case, if g of n, this here, is big O n to power log ba times log n to power k for some k, which is non-negative, then the function is big theta n to power log ba times log n to power k plus 1. So this is k here, this is k plus 1 here, okay? And in this case, the two procedures have the same order, okay? So you have the divide and conquer. So you divide the problem, the bigger problem, into subproblems, and then you solve the subproblems, and then you merge the solutions. Okay, so the splitting part, along with the merge part, and the solution of the subproblems, in this case, they are of the same order. Therefore, the T of n function has this complexity. This is the general setting, but in most resources, you would see this in a more simplified way. In fact, this is the scheme laid out in Rosen's book. And the master theorem can be stated in a simpler way. And this is quite useful in many occasions. Okay, so this is the general case. This one is the general case. And this one is a more specific case, let's say. Doesn't cover all the cases, but it's useful for a lot of situations. So, and it's also easier to apply, easier to remember, and therefore some people prefer this approach. So in this way, you see Tn equals a times Tn over b plus c times n to d. Now, the function g of n is specified here, c times n to power d. So it's sort of a polynomial function. You can also have other terms which are upper bounded by n to power d, like n to power d minus 1, n to power d minus 2, etc. But this is the general case, and also assuming that t1 is constant, n equals b to power k for some positive integer k, again without loss of generality. And a should be at least 1. It's an integer because that's the number of sub-problems you solve. You need to solve at least one to be for this to be a meaningful algorithm. And b here again is greater than 1 because the sub-problems should be smaller than the original problem. C should be positive because you don't want a negative number of operations in the merge step. And of course, D is a non-negative exponent. In this case, compare A with B to power D. Okay, A with B to power D. This, in fact, corresponds to comparing D with log B A. Okay, so it's not that different, but this is a simpler expression. So if A is greater than B to power D, then the complexity is n to power log BA. If they are equal, we have theta n to d log n, and if A is smaller, then the complexity is n to power d. There are many examples for this, both in Rosen's book and also online, and this is one of the famous ones for any divide and conquer resource. I have seen a lot of web pages that reference this document. It's one of the, let's say, worksheets of MIT Computer Science Department. You can take a look at this. There are a number of examples for all of the cases here, and some examples where the master theorem is not applicable. So you can see in which cases you cannot use the master theorem also. So I recommend you to also have a look at this document.